Hello friends, so today we are going to solve 4 questions, and these 4 questions are from you can say electrostatic, and with respect to that electric potential. Okay. In 1 second. Okay. So first question, we are given that a spherical shell with charge q uniformly distributed throughout its volume has inner radius r1 and outer radius r2. Calculate the electric field as a function of r, where r is from 0 to infinity. And part B is there. In part B it states that what is the potential at the center of the shell. You can let r2 is equal to r1, okay, and r1 is said to be equal to r. So this is the basic question. So in part A we are given, or in part A and B as well, so we are given the basic figure with that we have a shell, and that shell is having a inner radius of our r1 and outer radius is of r2, and we are given that there is a uniform charge distributed throughout its volume that is given as q. Okay, so we have a charge q that is uniformly distributed. Okay, so this is basically a shell. And so we know that in case of the spherical shell, there will be a uniform volume charge density between the inner radius as well as the outer radius. And let us say that uniform charge density is our rho. So we start from there only, and we say that for spherical shell, spherical shell with uniform charge density, uniform volume charge density, uniform volume charge density between r1 and r2, between inner radius r1 and outer radius r2, and let us suppose that is our rho. Okay, so we can write the formula for rho. So this rho will be equal to our total charge and the volume of this shell. Okay, that will be our 4/3 pi, and the difference between the radius, their cube, r2 cube minus r1 cube. So for the sake of simplicity, we can just move this 3 into the numerator. Okay, so this is our volume charge density for our shell, and we need to find out the electric field. So we can divide this entire shell into 3 regions. We can call the region, this is region number 1, region number 2, and the final one is our region number 3. So we divide this shell into 3 regions, And in order to find out the electric field, we are going to use the Gauss law, the simplest one. So we start with region 1, and for region 1, our Gauss radius, that is our R, is less than our R1. And within this region, we know that there is no charge enclosed. So you can say no charge enclosed, or in simplest we can say that our Q enclosed is equal to 0. Therefore, we can write that electric field will be equal to 0. Now we come to our region 2. For region 2, the Gauss radius or Gauss region is greater than our inner radius but less than our outer radius. And from here we can say that by Gauss law, let us suppose the charge enclosed is given as Q enclosed. Therefore, we can write that our Q enclosed will be equal to the charge density and the volume. This is our R cube minus R1 cube. Okay, because our so this is our R1 and this is our R2, and we have assumed a Gauss surface somewhere here which lies between, okay, and its radius is our small r. Okay. So we get the Q enclosed, and we can write this in the form of the given charge also, because the given charge is given as Q. So we can see this Q enclosed. We are going to get this as our Q times our R cube minus R1 cube divided by R2 cube minus R1 cube. Okay. And now we can easily find out our electric field. Okay. So you can say our electric field times our 4 pi r square will be equal to our Q enclosed divided by epsilon naught, which is our Gauss law. And from here we can say that of electric field at a distance r, we are going to get this as our, now we can just substitute the values. Okay, let me do it. So we can just substitute the values. Our Q enclosed is our Q, and this comes as our R cube minus R1 cube divided by R2 cube and minus R1 cube. So we can write this as, okay, and I forgot here, this is our, sorry, and this is our epsilon naught. Therefore we get that the value of electric field will be equal to, this will be Q upon 4 pi epsilon naught, and we have our R cube minus R1 cube, R2 cube and minus R1 cube, and times 1 upon R square. So this is the value of electric field in the region number 2. Now we come to our region number 3. Region 3, when R, that the Gaussian surface is having a radius that is greater than our outer radius, that is our R2. Okay. So in this case, the charge enclosed which is our Q enclosed will be equal to value of our Q, because now the Gaussian surface, so this is the inner radius, this is our outer radius, and the Gaussian surface is somewhere here. So now, so this is our Gaussian surface radius R, inner radius R1, and outer radius our R2. So now the Gaussian surface is enclosing the entire charge, that is our Q. Okay, there is no distribution of the charge like in our second case. Thus, we can write it as our electric field, and we have this as 4 pi r square will be equal to Q enclosed upon epsilon naught. Q enclosed is our Q upon epsilon naught. Therefore, we get that electric field at a distance r will be equal to Q upon 4 pi epsilon naught and 1 upon r square. So we got the value of our electric field. Now we can write this electric field in a piecewise form also. Okay. So we can say that the electric field is going to have 3 values depending upon the region. First value is our 0, and that 0 is when our value of Gaussian surface is greater than 0 but less than our R1 inner radius. And then it is going to have a value of our Q upon 4 pi epsilon naught, and this is our R cube minus R1 cube, R2 cube minus R1 cube times 1 upon R square. And this is when our Gaussian surface is lying between our R1 and R2. And finally, we are having this as our Q upon 4 pi epsilon naught 1 upon R square when our Gaussian surface is having a radius that is our greater than R2. So these are the 3 values of our electric field. This is sometimes also called as a piecewise form. You can call this as a piecewise form. This is a piecewise form. And now we are going to find out part B, and in part B we are supposed to calculate the potential. So in part B we are supposed to find out the potential at the center, and in that case we are given that R2 we can say that is equal to over twice of R1, and our R1 is equivalent to our R. Okay. So from here we can say that we can take that our R2 is equal to twice of R, because everything we are going to find out will be in terms of R, otherwise there will be too much of the variables or parameter will be there. And so for that we are going to take that the potential voltage at the infinity is equal to 0. Okay. And we are supposed to find out what will be our potential at the center. This we are going to find out. And like in first case, we already know when our Gaussian radius is less than our inner radius, that's R1, the value of electric field is equal to 0. Therefore, we can easily say that potential inside is our constant. So we can say that whenever r is our less than our r1, and here r1 is our r, we have already mentioned it, okay, and it is greater than or equal to 0, the value of electric field is equal to 0. Okay. From here you can easily say that the value of the potential will be our constant. Okay. So it means value of the potential at the center will be equal to value of the potential at our r. It means the inner is going to have the same potential. Okay. So this is our inner part whose radius is our r1, but in this particular case we have taken r1 is equal to r. So within this the value of radius is constant. Okay, so means whatever the radius, whatever the potential is at v is equal to 0, same potential is at v is equal to r. Okay, that's the meaning of this. Now we can easily find out our v of r by the integration, that is our normal process. So we can say that the potential at radius r will be equal to integration, and this is our E of r prime and minus d of r prime. Here r prime is we have taken as another variable in order to differentiate it from r, because r we have used multiple times. Here also we are using r. Okay. And so just in order to differentiate, we are going to take a new variable, that is our r prime. That is the, here will be our you can say Gaussian radius. Okay. And the limits will be from our infinity to r. Okay. So we are going to integrate inward from infinity. Okay. So we are going to move from infinity to the our spherical shell. Okay. And because of this negative we can just rewrite. So this will be equal to our r to infinity, and this is our r prime and derivative of our r prime. And we can, because here we are having two spheres. Okay, so let me, we have two shells, not spheres. Okay. So this is our outer part, and the outer part is basically given as our r2, but in this particular case this is our 2 is equal to r1, twice r1 rather, and that is equal to twice r. So we can just divide or split this integral into our two regions. So in region our r, which is less than equal to our r prime and less than equal to our 2r. Sorry, let me take our outermost first, much more easier because we are coming from the infinity part. So we can say that we have a region r prime that is greater than our 2r. Okay. Therefore we can say that our integral, and for the Gaussian surface of our r prime, and r prime means the Gaussian surface is somewhere here. If this is our Gaussian surface having a radius of our r prime, so in this particular case the entire charge will be enclosed by the Gaussian surface, that will be equal to our q. Therefore we can say that our, we get this as our 2r to infinity, and we get q upon 4 pi epsilon naught 1 upon r prime square and dr prime. Okay, because we already know this particular relationship. Okay, here only difference is that the Gaussian is we have taken as r prime, and r2 has been replaced by 2r, okay, for part B. So this is the only difference. And so we can just sort it out and this is will be giving us q upon 4 pi epsilon naught times 1 upon 2r. Okay. And now we come to our second region, and the second region is our r, which is less than equal to our r prime and less than equal to our 2r. Okay. So we already know this region is our this one. Okay. Because in this case also r1 is equal to our r, r2 is equal to our twice r, and this r we have taken it as a r prime. So the value of electric field is already known to us. Therefore, you can say that our electric field is our, we already know, let me write it in terms of our r prime. So this is our 4 pi epsilon naught. This comes as a r prime cube minus r cube, and the denominator we are going to get this as our one second. Yeah, denominator we are having this as a r2 cube and r1 cube. Okay, so we can write this as our r2 cube will be equal to twice r cube minus r cube and multiply by r prime square. Therefore, we get that the value of electric field will be equal to our q upon 4 pi epsilon naught, and this is our r prime cube minus r cube. So this will be coming as our 8r cube, sorry, not 8 but 7r cube. 7r cube multiplied by r prime square. And now we can just, you can say, sort it out with respect to our the integral part. So we can say the integral, and that is going to vary from r to 2r, and we are having this as a electric field r prime and dr prime. So we already know the formula. So this is q upon 4 pi epsilon naught 1 upon 7 r cube integral r to 2r, and this comes as our r prime minus r cube upon r prime square and derivative of our r prime. And so we get that the solution of this integral will be equal to our q upon 4 pi epsilon naught times 1 upon 7r. So we can say that our potential at 0 at the center will be equal to potential at the radius r, and that will be equal to the summation of the both the potential. That is our first part, and first part we are having 1 upon 2r. So this comes as 1 upon 2r, and second part we are having 1 upon 7r. Therefore, we get that our this will be equal to over 9, and seven 14. Okay, so this will be coming as 9 times q and 56 pi epsilon times r. So this is our potential at the center. Okay. Next question. It states that consider a ring with charge q, radius r. Let point P be a distance x from the plane of the ring along the x-axis through its center. by adding up the contribution from all the pieces of the ring, find the electric field at the point P. Part B, in the same manner, find the potential phi of x at point P. Part C, show that electric field is equal to negative of the derivative of our flux. Sorry, not flux but potential. Okay, so this phi is the representation of our potential. And part D, if a charge minus q with a mass m is released from rest far away along the axis, what is its speed when it passes through the center of the ring? Assume the ring is fixed in its place. So this is, especially the part first and second, are more like of a traditional way. Okay, we already know their formulas as well as the equations. Okay, but it is asked in a little bit different way, so we will try to solve it. Okay, so we are given that we are having a ring and there is a point P along its axis. Suppose this is a point P somewhere here, okay, and its distance from the center is, let us suppose, given as our x, and the radius is our r. So we consider a small element dq and try to find out what will be the value of the electric field because of this charge dq at point P. Okay. So the direction will be somewhere like this. So we can divide this our electric field, let us suppose that is our dE, into two components. Okay. So this component we can say is our x component and this is our y component. So there will be a symmetric, you can see, element which is having the same charge dq just opposite to it, and because of this the electric field at point P is, let us suppose, in this direction. Okay. So once again we can divide it into two components. This will be also our dE, so this will be our x component and we are going to have this is our y component. So our x component are going to cancel out each other. So only part that will be left will be the vertical component and the individual vertical component, and that will be their addition. Okay. And let us suppose this distance is given as r, small r, which will be equal to r square plus x square and square root. Okay. So this is the basic. And so we start that our, for a small element dq, for element dq, okay, we can write the field, that is our dE, will be equal to 1 upon 4 pi epsilon naught, and this is our dq upon r square. So like I said, only the vertical component will be left, the horizontal component will be balanced out. Okay. And so the component that will be left is our vertical component, and that will be equal to our dE cos of theta. Okay, if this angle is theta. Therefore we can write that dEy will be equal to our value of dE, we already know, is 1 upon 4 pi epsilon naught, and this is our dq and r square, and cos of theta will be equal to our x upon r, and our r is our r square plus x square. Therefore we can write that our value of our electric field will be equal to our 1 upon 4 pi epsilon naught, and this is our x times dq r square plus x square and whole raised to power 3 by 2. Now total electric field E at a distance of x will be equal to the integral of our dy, and we can simply put it, we get this as our Ex will be equal to this will be equal to our x upon 4 pi epsilon naught 1 upon r square x square 3 by 2 and integral of our dq, and the integral of this dq will be equal to nothing but a total charge q. So we get that electric field at a distance x will be equal to our 1 upon 4 pi epsilon naught q times x r square plus x square 3 by 2. And if value of charge, that is our q, is greater than 0, then this direction of electric field will be away from the ring. Okay. So this is our ring, so the direction of electric field will be away from the ring, okay, if the value of charge is greater than 0. Okay. So it's a direction away from the ring. Okay. Now we are going to find out the electric potential. So you can see potential from dq potential from small charge dq, let us call this our d phi, and that is equal to 1 upon 4 pi epsilon naught charge is our dq and divided by the distance, that is our r. Okay. And since all elements, because it is the point is at equidistant from the entire ring, therefore we can say that our potential at a distance x will be equal to 1 upon 4 pi epsilon naught, and this comes as our value of r is r square x square and square root, and once again the integral of our dq. Okay. And this dq is nothing but our q, so we get this as 1 upon 4 pi epsilon naught q upon r square plus x square and square root. So this is the value of our potential at our x. Okay. Now in part C, it says that we have to prove that the electric field is equal to derivative of our this potential. Okay. So we simply differentiate it. So we get this our derivative of our potential will be equal to, and so we get here d of our dx 1 upon 4 pi epsilon naught, and this is our q, we can write this as r square plus x square and 1 by 2 minus 1 by 2 rather. Okay. And so we get this as our d phi upon dx will be equal to our 1 upon, and this will be coming as our minus 1 by 2. Okay. And one second, yeah, so this will be coming as our, this will be our minus 1 by 2 and minus 1, so that will be giving us 3 by 2. So we get this as our 1 second, yeah, so we get this as our q upon, you can say 1 upon 4 pi epsilon naught q, and this comes as our minus 1 by 2, and we get r square plus x square. This will be our 3 by 2 and the derivative of our x, that is our 2x. So here this 2 and 2 cancels out. So this we get is nothing but our electric field at a distance of x. This negative sign we already have it. So this we have proved. And in part D, it says that we have released a charge that is a minus q from a rest from a distance. Okay. So we are going to use the energy conservation. So part D, okay. So we start with our energy conservation. And let us write our initial energy. Initial energy that is at infinity because it is very far. And it is starting from rest, so kinetic energy will be equal to 0 and our electrostatic potential energy will be also equal to 0. And we know that our potential at the center of the ring, that we already know. So you can see our potential at center of ring is our phi 0, and center of ring we can easily put the value of x is equal to 0 in case of our potential equation. So we put substitute here x equal to 0 and we get this as 1 upon 4 pi epsilon naught q upon r. So this is the potential at our center of the ring. Therefore from here we can easily find out what will be the potential energy at the center. So we can say the potential energy at the center, let us call this as our UF, and this UF will be equal to our charge, that is our minus q, which is coming from infinity, and our potential at the center. Okay, so we get this minus 1 upon 4 pi epsilon naught. We have this as q upon q times capital Q times r. And from energy conservation, you can clearly see that the summation of the initial energy should be equal to summation of our final energy. And as it is coming to the center, so it is going to obviously going to have some kinetic energy also. Okay. So we can say our kinetic energy at the center, let us call this our kf, and that will be equal to half mv square. So like I said, our initial energy plus should be equal to our final energy. Okay. And initial energy is equal to 0. So from here we can say that our kf plus uf will be equal to 0. So we get that our kinetic energy final will be equal to negative of final potential energy. Now we can just substitute the values. So this comes as half m v square will be equal to minus 1 upon 4 pi epsilon naught, and this is q into q times r, and therefore we can write that the velocity at the center will be equal to 2 upon m, and this is a q, capital Q 4 pi epsilon naught times r and its square root. So this will be the value of the velocity at the center when the charge of minus q is released from the rest at certain distance, that is very far, which is our infinity. So this was our disk, it is the center, and charge minus q is released from rest somewhere here. So when it reaches the center, its velocity is given as our v, and this is the value of the velocity. Okay. Next question. It states that the following vector function represents a possible electrostatic field: x component, y component, and z component. Calculate the line integral E from the point 0, 0, 0 to the point x1, y1, 0 along the path that runs straight from 0, 0, 0 to x1, 0, 0 and then x1, y1, 0. And part B is there. Make a similar calculation for the path that runs along the other two sides of the rectangle by the point 0, y1, 0. So indirectly, this question is saying that our this line integral, or we can say that our possible this electric field, okay, is our, or we can say we are talking about the conservative nature of our electric field, okay, which is path independence. There is no path dependence of our electric field as long as our initial and final points are same. So this is the basic. Indirectly it has asked this question. Okay. And so we are given that we have electric field E, which is having the three components: x component, y component, and z component, okay, and which are given to us. X component, y component is given as our 3x square minus 3y square, and z component is given as our 0. Okay. So in our part A, the path is given as starting from 0, 0, 0, and then it moves to x1, 0, 0, and then it moves to x1, y1, 0. So let us say this point is our A, this point is our B, and this point is our C, and we can just plot it approximately. So we start with our point A, which is our 0, 0, 0. Point B obviously lying on the x-axis. So this is point B, which is our x1, 0, 0. And then we move to point C, which is our x1, y1, and 0. So the path starts from A to B to C. Okay, so we are going to divide into two segments. This is segment number 1 and this is segment number 2. Okay. So we can say for segment 1, which is from A to B, okay, which is along x-axis, okay, and A to B is our along x-axis. So obviously the value of y is equal to 0, or we can say that our value of dy will be equal to 0. And the basic formula of electric field, we already know that E dl, in this case our x component will be our Ex times dx. Okay. There is no need to find out the y component because dy is equal to 0. Okay. And therefore the x component is given as 6xy. Okay. So this is our 6xy. Okay. But we have to remember that value of y is equal to 0. So we substitute value of y equal to 0. So we get this as 6x times 0 times dx, giving it equal to 0. Okay. So it basically means that our line integral of our electric field is equal to 0 when we move from 0, 0 to x1, 0. Now we come to a segment 2. You can say for segment 2, which goes from B to C, and the value of dx is equal to 0. Therefore, we can write that our E dot dl will be equal to our Ey times dy, and Ey is our, this comes as a 3x1 square minus 2y square dy. Now we can simply integrate it from our 0 to y1, and therefore we get this as our 3x1 square y1 square minus y1 cube. Okay, y1 cube. So it means for this entire path A, B, C, A to B to C, okay, you can say that our line integral will be equal to the summation of the two. First path is giving us 0, okay, so we get this as 0 plus 3 x1 square y1 square minus y1 cube, and we can write this as equal to 3x1 square y1 square, sorry, not y1 square but y and minus y1 cube. So this is for our path A to B to C. Now we come to our part B, and in this part B it states that it is moving from our 0, 0, 0, okay, other path. So once again it starts from 0, 0, 0, and then it moves from 0, y1, 0, and finally it comes back to same position, that is x1, y1 and 0. So initial point is our A, final point is our still C, and the middle point is, let us suppose, our B prime. That is a difference here. And we can just once again make an approximate plot. So this is our point A, which is having 0, 0, 0. Then it moves to B, which is our 0, y1, 0, and then it moves to point C, which is our x1, y1 and 0. Okay. Once again, we are going to say this is our segment 1 and this is our segment 2. Therefore, we can say from our A to B, okay, that is our along y-axis. Along y-axis, and obviously value of x is equal to 0, or we can say the value of dx is equal to 0. Therefore, our line integral will be equal to our Ey dy, and Ey we already know is our 3x square minus 3y square. So this is our 3x square minus 3y square, but we have to remember that value of x is equal to 0 times dy. Okay, so we substitute here, this term will be equal to 0. So we get this will be equal to our and derivative of dy, and we get this as minus 3y square times dy. Now we can just integrate it. So we get this as integration, and it is moving from 0 to y1, so minus 3y square and dy, which gives us minus y1 cube. And we come to our from our b prime to c. This is from a to b prime, and this is our horizontal line at y is equal to y1. So we have a horizontal line at y is equal to y1. So obviously dy will be equal to 0. Therefore we get that our E dot dl will be equal to only the x component, and x component is our dx, and point is our 6x y1 times dx, and we can just integrate it from the limits 0 to x1. So this comes as our 3x square, 3x1 square and y1. Yeah, that's all. So it means for our second case, we get that our line integral for our second case is also equal to our first x1 y1 minus y1 cube. Okay. And this is same as our this path. Okay. So we get this was our a to b prime to c. Okay. And this is nothing but our a to b to c, which tells about our path independence. Okay. This is the indirect way it has asked for. Now from here we can just find out our potential also. Okay. So we can say the potential that is about phi, and it is going to have x, y and z. And we know that the potential by definition is equal to negative of our this line integral. And so we are going to use the result from origin to any point xy. So we can say from origin to xy, we get, because z is already 0, so we can say our potential for xy will be equal to minus, and this comes as our 3x square y minus of our y cube. And if we choose that our initial potential, that is potential at origin, is equal to 0, therefore we can say potential with respect to our x, y and z will be equal to our y cube minus 3x square times y. And next question. So it states that each of the objects described below has a uniform volume charge density as rho. There are no other charges present in addition to the given object. So based on this we have we can say 3 different objects. A rectangular slab has a thickness in x direction and infinite extent in the y and z direction. Show that E of x is equal to rho x upon epsilon naught inside the slab, where x is measured from the mid plane of the slab. Second object is our an infinite long cylinder has a radius r. Show that E of r is equal to rho r divided by 2 epsilon naught inside the cylinder. And part C, a sphere has a radius r. Show that E of r is equal to rho r 3 epsilon naught inside the sphere. And D part, given that above three setups involve the same charge density, that is rho, why do they give different results of the electric field? So this is the basic question. Question is little bit easy, statement is little more complicated. Okay. So simply we are going to use our, you can say, Gauss law and find out all the options. You can say solve all the options. So we have a part A, and so we have a, suppose a rectangular box is there, we have a rectangular box and whose area is, suppose, is our A. Okay. And it extends from minus x to plus x. So from here we can easily find out the flux, that is our phi, will be equal to our EA times plus EA, double side. Okay, so this comes as our 2EA, and the charge enclosed is, suppose, our Q enclosed, which will be equal to our charge density and our 2x times A. And so by Gauss law, gives us that 2 times electric field area will be equal to charge enclosed, that is our 2x times A upon epsilon naught. So we get the electric field is equal to rho x upon epsilon naught. This is our part A. Then we come to a part B, that is our infinite cylinder. So here we consider a Gaussian surface and this Gaussian surface is having a radius which is our less than r, and this Gaussian surface is also cylindrical. So we can just draw an approximate figure. So this is our original cylinder whose radius is given as capital R, and we consider a Gaussian surface which is having a radius of small r, something like this. Okay, so its radius is a small r which is less than our capital R, and the length we have taken this Gaussian surface is capital L. Therefore we can write that flux, that is our phi, will be equal to our E times 2 pi r L, and the charge enclosed that is Q enclosed will be equal to our charge density and the volume charge density, r square L. Simple. Now Gauss law gives us that electric field N times 2 pi r L will be equal to the charge enclosed, which is rho and pi r square L divided by epsilon naught. So this gives us that the value of electric field is equal to rho r upon 2 epsilon naught. Okay, and in last part is of a sphere of radius r. Okay, this is much more easier, and so let me finish the sphere first, then I'll come back to the question. Okay. So we have a part C, and part C is our sphere. Okay. So in this case we take a Gaussian surface whose radius is less than our capital R. So this is our sphere, and Gaussian surface we have taken something like this of radius small r. And so once again our flux is equal to our E 4 pi r square, and charge enclosed, that is Q enclosed, will be equal to charge density and 4 pi r cube. So by Gauss law we can say that our electric field times 4 pi r square is equal to, this comes as a rho 4 by 3 pi r cube and epsilon naught. So we get that the electric field is equal to rho r upon 3 epsilon naught. So we get that the numerical factor of the electric field for all the theory, that is our slab, our cylinder, and our the sphere, even though they all have the same charge density, that is our rho. Okay. And this basically we can say that it happens because of the way the electric field is going to behave. Okay, or we can say spread out. Like in a slab we have two faces of our area, okay, one at the top, other at the bottom. Okay. For our sphere we know, oh, sorry, not sphere but slab, it is having a two areas, something like this. Okay, one at the bottom and other one at the top. So this is one first area and this is second area. And our cylinder, basically the you can say field line spread through the circumference, and the sphere it spread through the surface area. Okay. So this is a numerical, you can say, factor that comes into the picture is 1 upon epsilon naught, 2 epsilon naught, and 3 epsilon naught. And so these were the questions for today. And in particular, like for our ring, we have to, that's very intuitive part. So this is our ring, okay, and we are interested in a point. Okay, so this point is somewhere here. So we take a, you can say, our, you can say a small charge element which is somewhere here, that is our dq, and try to find out, because of this dq, the electric field at this point P. Okay, suppose this our charge is positive, so electric field direction will be somewhere in this direction, that is our dE. And if we pull it downward, and this is our radius r, and this angle will be our theta, then there will be a, you can say, symmetric point with respect to this dq that will be somewhere on the opposite part. Okay. And if this distance is our r, so symmetrically this distance will be also equal to r, and the electric field will be in this direction. Okay, so let us call this as our first, and this is our second. So this will be electric field due to first, and this will be electric field due to second. And we can divide the respective electric field into two components. So this will be first x component, and this will be first y component. And once again this will be our second x component, and this will be first y component. So from here we can clearly see that our x component are balancing out each other. Similarly, this will be true for all the symmetric elements. Suppose somewhere here we have taken as element, okay, and correspondingly there will be other elements somewhere here, whose distance will be also equal to same. Okay. And please remember, this ring is in the xy plane. Okay, and this point P is perpendicular, that is in the z axis. So the net electric field will be the summation of our first component plus because of our second y component. Okay, and this is our angle theta, so this angle will be also equal to theta. We can just, with the help of the geometry, we can easily find out. So the electric field, net electric field, will be always in the y direction. Okay, and their sum, so this will be our dE, and in order to find out complete electric field, we simply integrate it. Okay, so this is the easier one as compared to ring. So in case of the symmetricity, it is very helpful. Okay, we take one end and symmetric point to the other end, and because of that, these two components are going to cancel out each other. So only component will be left is in vertical direction. And in some of the cases, I think yesterday we did a question on that we were having a dipole and it is given as our plus q. Here our charge was our minus 2q and this charge was our plus q. And in that case also, it was mentioned that the net total charge at this, where the two dipoles meet, is given as minus 2q, and we are supposed to find out electric field at the point which passes through this. So this is the indirect representation of our ring. Okay, because ring we take two elements which are symmetric to each other. So if we join them, so they come something like this. Here only the value is different. Okay, so this is, and once again the electric field because of this will be in this direction, and because of the other charge will be in this direction. So net electric field because of these two will be in this direction, and because of this minus, it is going to have a electric field here also. So this will be because of minus. Okay, so there are multiple combinations in which this ring concept can be used. So this completes all the questions for today. Thank you.